So I've prepared this midterm review for you all because there could be a GSI strike this week, but I know you all have a midterm this week. So I just wanted to prepare something before the strike officially starts so that you have some reference material to help you out in addition to everything already online. So I've prepared a few sample problems I'm going to work through, but please remember that your midterm covers lectures 23 through 32 and homeworks 9 through 12. So this will be just a few selected problems from certain sections. And I thought it would be useful to walk through some of these, but please remember that this is a non-extensive list and to review additionally. Make sure you're just covering all the material that's going to be on the exam. So let's get started. This first problem is from homework 12, number 5, and here we want to evaluate the definite integral. So my first step here is going to be to rewrite this so I can get it into a form that's a bit easier to work with. So after pulling this x to the negative 1/2 up to the numerator, I'm going to distribute it to each term. And now this is something that's a lot easier to work with. So from here we can go ahead and take the antiderivative. So remember the process for that is adding 1 to the exponent and then dividing by our new exponent. And since this is a definite integral, I want to remember to include the bounds here so that I don't forget to calculate over these bounds. Now I can go ahead and simplify this expression a bit before evaluating. And now I'm ready to evaluate. So we're first going to plug in our upper bound 8 everywhere that there's an x in this expression. And then I want to subtract the value of our expression when our lower bound 3 is plugged in. Okay, so from here, I went ahead and I used a calculator to solve this. But remember, on the exam, you'll have nice, easy numbers to work with that won't require a calculator. So you'll be able to solve anything that we give you to evaluate. You can do it without a calculator. Okay, now we can move on to the next problem. This is also a homework problem from homework 12, and this is number 10. So here we want to evaluate the indefinite integral. And this expression looks kind of messy to deal with, but it looks like it's a good contender for u substitution. So let's try to work with this problem using u substitution. So I'm going to let u equal this expression inside of my sine function. And then we need to figure out what du is by taking the derivative. And now we have everything we need to rewrite this expression. So to make this a little easier to see, I'm going to rewrite this just by switching these terms around. And now let's plug everything in. So I can see that my u is equal to e to the 6x, and that's what's inside my sine function here. So I'm going to substitute in u inside of my sine function. And then we figured out that our du should be equal to this expression, and we can see that we have that right here. So I'll substitute all of that in for du. Now this is something that's much easier to evaluate, so let's go ahead and take the antiderivative. That's just going to be negative cosine of u. And remember, since this is an indefinite integral, we want to add a constant. And now our final step here is to just resubstitute in everything in terms of x. So I'll put e to the 6x in for u, and that will be our final answer. Okay, let's move on to the next problem. This is another one from homework 12. This is number 14, and this is another u substitution problem, but it's a little trickier than the last one. So here, I'm going to let u be what's inside of my square root function. And let's figure out what du has to be by taking the derivative. So since we found that du is equal to 8 dx, I'm going to take a quick look up at my whole function in here, and I see this dx part, but I don't see any 8 in my integral. So what I'm going to do is solve for just dx so that I can substitute in everything equal to dx into my integral. So I can do that by just dividing by 8 on both sides, and we end up with dx equal to 1 over 8 times du. Okay, then now since we're working with a definite integral, we also need to think about our bounds here. So when x is equal to 7, u will be equal to 8 times 7 minus 7, which is just 49. So this is going to become our new upper bound. And then when x is equal to 23 over 8, u becomes 8 times 23 over 8 minus 7, which just becomes 16. Okay, so now we have all of the information we need to rewrite this as a u substitution problem. So this is what we're starting with. I'm going to factor out this minus 5 as a constant. And now we can plug everything in. So remember our u is equal to 8x minus 7, which is what's inside of our radical here. So let's put u there. And then we figured out that our dx here is going to be equal to 1 over 8 times du. So let's add that expression in. And now we want to rewrite our bounds. So we figured out that our upper bound should be 49, and our lower bound should be 16. Okay, now I can go ahead and simplify this a bit. So I'm going to factor out that 1/8 as a constant, and rewrite this as u to the negative 1/2. Okay, now I can take the antiderivative, and now we can evaluate on our bounds. So we end up with negative 15 over 4. So that's an example of doing u substitution with a definite integral. Okay, the next problem that I've selected is from homework 11, problem number 18. So we can treat this problem as a u substitution as well. So let's let u equal 2x in this case. Then our du becomes 2 dx. And let's solve for dx since I don't see this 2 term in my integral. By dividing by 2 on both sides, we get that dx is equal to 1/2 du. Now we need to figure out our bounds. So when x is equal to 1, u is equal to 2 times 1, which is just 2. And when x is equal to 0, u is equal to 2 times 0, or just 0. Okay, now we have everything to plug in. So we can rewrite this with u instead of 2x, and 1/2 du instead of dx. And we can remember to put our new bounds in. And now we can simplify and solve. So if you don't remember how to take this antiderivative, it might be a good one to write on your cheat sheet for the exam. So our final answer ends up being 4 over the natural log of 3. Next problem. So the rest of these are from different practice midterms. So here we need to find f of x, and we're given the second derivative of x and some information about the first derivative and the function itself. So we're given the second derivative, and I want to find f of x, so I'm going to take the antiderivative to get there. So the first time I take the antiderivative, we get x squared over 2 minus cosine x, and plus a constant c. Let's call this c1. And now we can use this information that we're given here, that f prime of 0 is equal to 0. We can use that to solve for c. So I'm going to let x equal 0 in my first derivative here, and let that whole thing equal 0. Then this term just becomes 0. Cosine of 0 is 1, so we have negative 1 here, plus c1 equal to 0. So that implies that c1 is equal to 1. So we can rewrite our antiderivative as x squared over 2 minus cosine of x plus 1. Okay, so now we can go ahead and take the antiderivative of our first derivative here in order to get our function. So that's going to be x to the third over 3 times 2 minus sine of x plus x and then plus another constant here. We'll call it c2. Now we can use the fact that our function at x equals 0 is equal to 2 in order to solve for that second constant. So plugging in 0 for x here, and letting that all equal 2, we can now solve for c2. So all of these terms are 0 except for c2, so that tells us that our second constant is just equal to 2. So then our final function will just be x to the third over 6 minus sine x plus 2. Okay, moving on to the next problem here. Here we want to use Newton's method to approximate the solution of the equation cosine of x is equal to x. And they tell us that our initial approximation is 1, and they want us to find what the next approximation is. Okay, so first of all, we're given cosine of x is equal to x. Let's rewrite this as cosine of x minus x equals 0. And let's let that be our function, since we're finding a root of this equation. So remember, if we want to find our next approximation, Newton's method tells us that that's equal to our last approximation plus our function at that approximation over the derivative of our function at that approximation. So they tell us that our first approximation is 1. So then our function at that value is just going to be cosine of 1 minus 1. And then we're also going to need our derivative, so let's calculate that now. That's just going to be minus sine x minus 1. And at our approximation becomes negative sine of 1 minus 1. Okay, so now we have all these pieces here that we can plug into our Newton's formula. So that just becomes 1 plus cosine of 1 minus 1 all over minus sine of 1 minus 1. And since we don't have a calculator on the test, we can go ahead and leave it like that. Okay, moving on to the next problem. Here we want to evaluate these two limits. So let's think about this first one here. If we were to plug in pi over 2 for x here, we would end up with the form 0 over 0. So that's one of the indeterminate forms that allows us to use L'Hopital's rule. So let's use L'Hopital's rule by taking the derivative of the top and the derivative of the bottom. So here we're going to get the derivative of our numerator over the derivative of our denominator. And now if we plug in pi over 2, we end up with 2 cosine of pi over negative sine of pi over 2. And all of that just evaluates to 2. Okay, so that's how we do our first problem here. And remember, for L'Hopital's rule, you can only use it if you have a form 0 over 0 or infinity over infinity. So now let's try to evaluate this limit. If we took the limit right off the bat, we would end up with sine of 0 over cosine of 0, which would give us 0 over 1. And that's not an indeterminate form, so we don't have to use L'Hopital's rule or anything else. We can just say that this limit is equal to 0. So it's important to remember when you can use L'Hopital's rule and what indeterminate forms are. Okay, moving on. For this problem, we want to find g prime of x, given that g of x is equal to this integral here. So we can use the fundamental theorem of calculus to solve this problem, but remember that the fundamental theorem of calculus is defined for some integral x as our upper bound, but here notice we have 3x. So let's rewrite this so that we can go ahead and use our fundamental theorem of calculus. So let's let g of x equal h of 3x, where h of x is equal to the integral from 1 to x of sine of t squared dt. Then h prime of x, we can use fundamental theorem of calculus here, which tells us that this is equal to our function with x plugged in. So then if we wanted to find g prime of x, we would want to take h prime of 3x and then use the chain rule to multiply this whole expression by the derivative of what's inside this part here. So this whole thing would be multiplied by 3. So we would have 3 times h prime of x, h prime of 3x. And that's our final answer.